Hey, what's up, YouTube? How's it going, hobbyists? Thank you all for being here, for watching. I hope y'all are having a great day. I just went live, so I imagine nobody's going to be in the chat for a moment. So if anybody's watching the VOD, please forgive the slow start. Feel free to jump ahead. Just hit the forward button until the iPad is up. That way you can very easily see when we're going to get started with the actual math. You can just keep fast forwarding or just hang out and chill and listen to me rant about random things. Okay, so discussion number 3. Once we get people in the chat, I will switch over once more, just reminding everybody about that. Air server is up on my computer. Hey, we got one person in the chat already. What's up, Jack Mac? How's it going? You beat me. You joined the discussion, or you joined the chat before I even wrote the title. Discussion number 3 for hobbyists. Thank you for being here, dude. Thank you for being a hobbyist. How's it going, man? Let's see. Do I want... Yeah, we've got some background music. I think background music is nice for this. Yeah, how's it going, man? Any questions? Anything that you want to work on or talk about from the section or the reading? If not, I could just pull some random topics or work problems. Looking forward. Hey, what's up, Tao family? How's it going? Good to see you. Great to see you. So, what next? Any questions? Thoughts, questions? Math or otherwise, really kind of Q&A of any kind. Recent changes, what is the ideal video length? That's one question. And how did you all feel about jumping around? Jumping forward to chapter interlude and chapter 16. That may have seemed confusing, but I guarantee you all, this is the structure that most college courses would take, actually. Oh, I'm working on a problem right now. Can't crack it. Awesome. Yeah, I think that should be priority 1. Priority number 1 should be questions. What problem do you want to work on? If y'all want to list problems in the chat, Tao family, if you have any problems that you want to work on after, I'd be happy to try to add them. I would like to prioritize problems from Lang. I could try this one, but it sounds like square x. I can try it, but I do want to prioritize the materials that prioritize the topics that we've worked. It looks like you wrote... Okay, let me see. I think I can copy this and then paste it directly. You wrote this. 1 over x plus h raised to the 1/2, which we can translate as the square root of the thing. And then 1 over 1 plus x with no space or anything in between. So I'm just going to assume that this is a multiplication, not an x, but a multiplication with 1 over 1 plus x. And then divided by h. Is this all divided by h? Like, this is... I feel maybe you're trying to say multiply by 1 over 1 plus x over h. I think that that's probably what you meant. I forgot a negative, not multiplication. Oh, minus. Okay, so this should be minus here, right? Okay, so this is a cool question. I do want to try to help you with this one later in the video, if that's okay with you, because I do want to prioritize Lang, and this definitely is not material that we've done yet in the course, but let's try to come back to this. I'll give this a big red to do and see if we can remember to come back to it. First, HHH tau family. This is kind of... I've never even thought of this, but look at this. I'm coming up with new ideas all the time. Here we go. Paste. Is this going to work? Let's see if it worked. Okay, well, the formatting got all kind of messed up, but can you give an equivalent word for whenever? Is whenever similar to the if part of a statement? Good question. Let's see. Do you remember a specific case? But I think that the answer is yes. Like, x equals 5/2 whenever 2x equals 5. I think that this is like a lot. You're talking about how to parse a logical statement. Something like this. Yes. You're talking about how to understand whenever in an English sentence. In symbols, this would say that 2x equals 5 implies that x is 5/2. Whenever is used as when this thing is true, then this thing is true. So whenever is like a backwards implication arrow. Whenever really is a backwards implication arrow. I think that that's what you're talking about. Oh, yeah, in the proof structure where you had made up words. Yeah. You're talking about the Jabberwocky example. By the way, it's an allusion to Alice in Wonderland, like the published book, Alice in Wonderland. That's what the Jabberwocky strange words were. Discussion number 3. So that one would have been in episode 6. Let me copy that. Yes. So I'm definitely pulling from other books, and that would be one that's a little slightly confusing or something. This one is definitely a less obvious example. I tried to outline how these statements break down, and what I was really writing was that A1, the occlusions make this a little hard, but oh my goodness. Okay. Oh no. See, what can I do? Here we go. Okay, so A1 is this first statement that you're asking about. Borogoves are mimsy whenever it is brillig, which is crazy. A crazy sentence. Whenever it is brillig implies that Borogoves... I wrote that wrong. Borogoves. If it's brillig, then if you have a Borogove, it is a mimsy Borogove. So, yes, as an English sentence, that is saying that brillig implies something about... Brillig implies the first part of the sentence. So, if I labeled these, it may have been more clear pedagogically, maybe, if I named these something like Borogoves, mimsy. Borogoves are B1, brillig is B2, maybe, and mimsy is M. Maybe I should stick to a convention that, like, one's numbers come earlier in the sentence, no matter what the implication arrows are. If I labeled the things this way, then my sentence that I wrote would be, brillig, like, more, written in the same order as the English sentence. It would be Borogoves are mimsy whenever it is brillig. It would be something like this, which is a little confusing often in math to write forward and backward arrows in the same sentence. Like a backward arrow is just a reverse implication. It just means B2 implies the rest. So that is really logically the same exact math sentence as this. B2 implies B1 implies M. I wonder if that helped, or if this... I mean, I chose to pull in this topic and this specific example, which is from a book that's super clear. B1 implies B2 from M. It's a slightly different, because what you just wrote was that mimsy implies stuff. But it's not mimsy implies stuff, but brillig implies stuff. Like, if I call this BM as, like, the fact Borogoves are mimsy, then typo, you meant what I wrote. Okay, cool. So the backwards arrow is the whenever, to answer your original question, and now I'm kind of getting somewhat into the weeds or something. But yeah, awesome, great question. Yeah, I didn't even think of defining, or the fact that I've used whenever in that moment, because I'm so used to mathematical language, which is why I think it makes so much sense to teach truth tables and write out truth tables and understand in symbolic logic the way that that I did in those videos, because the idea is that you should learn this stuff and then forget it. Like, the idea with symbolic logic of, like, doing truth tables, you should learn it, you should understand how we build these complex mathematical sentences, but then you forget it. Like, you want to go back to just writing English sentences, but the goal is to know how to be very precise in your language in a mathematical sentence. So the word whenever, what does whenever mean? It is that backward implication arrow. So all of those words, even though it's English paragraphs, they have very precise, rigorous, quote unquote, meanings and definitions. So yeah, that's a really excellent example that I didn't even think of. I'm so used to reading and speaking in English for math, and that's one that I forgot. Oh yeah, that is a technical term. Whenever means this thing implies this stuff. Yeah, great question. Great question. Let's see. Anything else about Lang? How were the induction examples and exercises? Did you all enjoy the? I just posted the logic episode. This morning? I just posted the next logic detailed video this morning. So I imagine you all haven't seen it. It's a little bit behind, I think. So I apologize that one was behind. But I could show what I did. I think I was just showing some lecture notes that you all haven't seen yet. In the new episode that just went up today, you just saw it. Yeah, sideways pi symbol. Yeah. Great question. So you can watch the video, but there are things that I think could have gone better in the video. What you're talking about is this, the sideways pi symbol. I love that. It's called the double turnstile, if you want to use the technical term for what that symbol is. It's not quite pi. Like pi has like a kind of curved top to it. The double turnstile, I don't know, it's got a vertical bar and then it's got two little spokes that pop out of it. I don't know. There's so many funny looking cool symbols that you get to learn in math. So that is called a tautology. A tautology is a statement that is always true. Like no matter... So in these logical statements like this one, this depends on the value of A, right? A can either be true or false. Or a better example would be a logic statement like A and B. There's going to be a lot of symbols in this that you probably haven't yet seen until you watch the episode. But this means A and B. This is true if A and B are both true. The AND connection or function, we could say, it's either every logical sentence, every logical expression is either true or false. So if we can write down exactly when it's true and when it's false, then we understand how that connective works. So I could just say false otherwise. But to give a truth table for this thing, we can use true and false or ones and zeros. I like ones and zeros because I'm a programmer, I guess. If one means true, then A and B is true if both are true, just like the word and. My name is John, and it is 1:18 p.m. where I am. That is a true sentence because my name is actually John, and it is 118. So the second case is false. That would be like, right now, it's already 119. So the sentence is now false. It is no longer 118. Right now, it's 119. So the sentence, my name is John and it is 1:18 p.m., is now false because the second part is false. So, anyways, this is a logical expression that sometimes is true and then sometimes is false. It depends on the values of A and B. On the other hand, another type of expression would be one that let's see. Yeah, A or not A. This is a good example. Read this and think of this as A or not A. The sub-expression or the atom A can either be true or false. Either Kaya or Luna, black or white, on or off, yes or no, true or false. In this first case, it is true or not true. Not true is what we mean by false. And the or function, either side needs to be true in order for this to be true. So this one is true. When A is false, then this is false or true. And the or function allows either side to be true. So then this one is also true. So therefore, by the way, this symbol with 3 dots and kind of a pyramid looking thing, we can pronounce as therefore. Luna, don't throw up on my backpack, please. Don't throw up on my backpack. Poor baby. Poor baby. Oh, poor baby. I'll have to clean that up. But she was about to throw up on my backpack. That's so gross. Okay, so first... Oh, poor baby. I don't know why... What's going on? Okay, I will clean that up in just a second here. Therefore, A or not A is always true. And we write, when a logical statement is always true, we call it a tautology. And we write this symbol, which means that it's always true that either A or not A is true. Lots of new words. Lots of new words when we're talking logic. This is actually newer math. This truly is newer math. Mathematicians have used these ideas in mathematical arguments for thousands of years. But logicians... Logic goes way back. Logic goes way, way back to the Greeks and before. Like, simple logic and logical arguments, and a lot of this stuff goes way back. But this level of mathematical formalism and trying to turn logic into a math field of its own, to try to model and understand mathematical arguments and try to answer questions like, when do we know if every mathematical sentence is provable? Like, provability and proof theory is a more modern type of math, and it's becoming increasingly more important. Like, in the 50 years since Lang's book was published, this stuff is even more important than ever. So it's part of the reason why I really want to add it to the book, even though Lang doesn't cover this as much. So that's a long answer to your question. Tautology is a logic expression which is always true. If we have a sentence like this, and that this is always true, if this is always true, then this is like saying that A is equivalent to B, or that A and B both imply one another. These are two different ways of writing the same logic sentence. And the video goes through a bunch of examples of tautologies in math. Like, we get things like associativity. We see associativity popping up again. This is, I'm going to say equals, but technically we should say tautologically equivalent, but I'm running out of space there. Let's move all that a little bit and shrink it or something, or move it down here. The fact that we can regroup parentheses with the and, with the idea of and, these two are equivalent logical expressions. Does that make sense? Any questions, anybody? I can try to come back to the algebra problem just to work that one really quick. Great question. Okay, so we wanted to subtract these two, and please let me know, Jack Mac, if I wrote it incorrectly. This looks a little tricky, but the first thing I would see is that in the first term, we would want to rationalize that term by multiplying the numerator and denominator by the square root of x plus h. Then the square root of x plus h multiplied by itself is x plus h. Let me know if you don't see that step, like how I rationalized the denominator. And then I would do 1 over 1 plus x over h, rewrite 1 as h over h, Now in the denominator, they have the denominator within the denominator, they have a common denominator, x minus h over h. So Luna, get off of my keyboard, please. Luna. Let's see. If you don't see this step, let me know. I would like to know, at what point do I lose people and things like that. Like, it's hard for me to judge based on, like, facial expressions or things. In general, we have this property that this is B over A. One way to think of this is that 1 divided by anything is the multiplicative inverse of the thing. The multiplicative inverse of A over B is the number that you can multiply with A over B so that when you multiply them together, they equal 1. Okay, yeah, I can explain rationalizing. Last thing I'll just say here is that when you take the inverse of a thing, that flips the numerator and denominator. So this is B over A. This is just like 2 inverse is 1 over 2. 1/2 inverse is positive 2 over 1. Or 3/2 inverse is 2 over 3. So that's how I got to this step, h over h minus x. You asked about this first step. What does rationalizing the denominator mean? Okay. I think a good example. I want to make sure that people understand simple examples, simpler. So something simpler than the problem that we're working. This is just a good general strategy. If you want to understand rationalizing the denominator, is that it? Let's start out here. If you need to rationalize a thing, then that means taking something that's not rational. To rationalize means something's not rational and now make it rational, right? Irrational to rational. This is all math that we haven't yet done in the series, but I'm very happy to explain this and work it. So what are the rationals? Here's the symbol for them, but they are the set of all fractions where A and B are integers. And you can add some extra requirements. B is not allowed to be 0, for example. You don't have an inverse of 0. So, like a few extra details there. But we want to take something that is not a fraction and turn it into a fraction. So, irrationals are included in the real The real numbers are all the fractions and the irrationals. Fractions and irrats. And the first classic example of an irrational number, which we haven't seen yet, but I have said this already in my videos, is square root of 2. Square root of 2 is not a rational number. It is a real number. In grade school, we just learned that square root of 2 has a decimal expansion and it never repeats itself. Therefore, it is not a fraction, and therefore it is a number that is not a fraction, and we call those the real numbers. You can prove that square root of 2 cannot be written this way, because if it was written this way, then you get a contradiction. Okay, so to me, in my opinion, this is the simplest irrational. So are you following my logic on like why I'm building this right now and trying to come up with an example? Like, I wonder if you're following my logic. And I'm coming from the fact that this word is rationalizing. To rationalize something, I just realized HHH Tau family is the person who asked, what does rationalize the denominator mean? I apologize. Jack Mac might have followed everything here. I just misread. Okay, so to rationalize a denominator means to take a denominator which is not rational and then convert it to a rational. Okay, so the simplest example I have is when x is the square root of 2. So if I want to convert the denominator of this number to a rational, pretty much the main tool that we have, which is just such an OP strategy, it's just so overpowered, is that you can multiply anything by 1. And we do this so much that we get used to this, and we just skip some steps. But you can multiply anything by 1 and you don't change the value. 1 is also the same as any number divided by itself, except for 0, because you can't divide by 0. Now, we can multiply numerator and denominator. Technically, we haven't done this yet. Here, let's do this with A, B, C, and D instead. A over B times C over D. If you multiply two fractions, you multiply across the numerator and the denominator. And we will prove that, I believe, in Lang. Like, we will understand this as a theorem. But that's the fact that I'm going to use right now. 1 times anything is itself. Square root of 2 times square root of 2 is the square root of 2 squared. And the square and square root of 2 are inverse functions. So the denominator, that can be one argument that or another could be that the square root of x is a number raised to the 1/2 power. So then square root of x is x to the 1/2 times x to the 1/2, and then use the fact that you can add fraction, that you add powers when you multiply together. So so we have seen this one. We have seen this math fact already in the rules for multiplication section. Yeah, typically we only say that you rationalize irrational denominators, yes. There's nothing wrong with writing this, and oftentimes it's simpler to keep a number written this way. But other times it can simplify a lot when you're doing an algebraic expression. So this denominator on the left has a square root, and then the fraction on the right does not. If I'm going to have any hope of combining these two into one term, I'm going to want to get rid of that square root so that I can add and subtract h's and x's. So we got to this point in the derivation. Now, well, let's keep that the same for a second. If I factored out a negative from the denominator, we'd have this. So factor out -1 from the denominator, and then negative, like minus negative, becomes a positive to combine those terms. Then square root of x plus h times x minus h over x squared minus. So if I multiply the first term by x minus h in the numerator and denominator, I get that. And then the second one I'd multiply by x plus h divided by yeah. Now I have a common denominator. I don't know how much better this is going to simplify. I think that this is not the worst possible way to write this if you just added those numerators. I don't know if your problem wanted you to show that this is a specific expression, or I don't know if this really... I don't see a way that this is significantly simpler. Oh, how do we know that square root of x plus h is irrational just because of the square root? Yes, because x can be anything. X can be any number, so taking the square root of most numbers would be irrational. Taking the square root of numbers often, but not always, gives you an irrational number. Yes. Like, there are only very few isolated specific cases where the The square root is not irrational. Good question. So, well, square root of 4 is not irrational. You gave me one example that is not. Square root of 4 is 2. But square root of 5 is not rational. Square root of 3 is also not rational. In fact, the square root of any prime we can prove is not rational. Can you do it with radical 1 plus x? Well, yeah, we got to this expression. So if h is 1, then you can substitute in 1 everywhere. Is that what you mean? Like radical 1 plus x? I think, yeah, I don't know what the original question was aiming to get you to prove or show, or like why you're computing this, or what the final, because it doesn't simplify to some like really simple nice expression. I think that this is as good as anything else. I mean, we could factor out a square root of x plus h. It doesn't make it a whole lot nicer, but I mean, we could see if we could keep going, but I don't know. Yeah, I don't really know where you're going with this. It seems like maybe a proof regarding a derivative. Are you in calculus or pre-calculus? Oh. Do you just want to simplify this? Or rationalize square root of 1 plus x? You just want to see this simplified? Which I should show this step, because what you wrote was negative 1 over 1 plus x to the 1/2 power. The square root sign means the half power of a number. It is, yeah, a number raised to the 1/2 power. Excuse me. Well, this, you can multiply the numerator and denominator by the square root of 1 plus x, and we get this. There's not really anything further that you can get to. Average rate of change with radical denominators. Yeah. That makes sense. When h is... Yeah, if you have like a function... that's maybe not the best example. if you have a function, you may want to find the average rate of change between 2 points. The average rate of change is the slope of this line. That would be the average rate of change between those 2 points. Then your function might have certain values. Oh, excuse me. Kind of, wait, let's see. -1 over 1 plus x raised to the 1/2. So the average rate of change would be, remember, average rate of change, or in general, rate of change is rise over run, or change in y divided by change in x. This is another way to write the slope of a line. mx plus b. This is some algebra that we haven't yet gotten to about the equation of a line. But excuse me, if people remember the phrase rise over run is the slope of a line, this is what they mean. Change, the delta symbol means change. How does the y value change compared to the x value of this function? Then the y values would be f of b minus f of a, and then the x values change from a to b. So the change in x is b minus a. Then the function that you gave me could, I don't see how to get to totally different denominators, but yeah, what you showed me is closely related to this. And that if you shrink that interval, it's kind of cool that I can like literally copy the exact same curve, and then maybe I made, oops. This is h. Like, let h be the distance between the 2 points. Then this point B would be a plus h. Then, what we can do is we can shrink the step size. If h is small, like if h was half as big, the new point would be like about here or so. And it looks like that's even like a slightly negative slope. If I took another one and made h even half of that, then we'd get, oops. This line, which has just ever so slightly more negative of a slope. And yeah, this is just a very, very key, important idea in calculus. If you take h to be incredibly small, then we get a rate of change that we call instantaneous rate of change. So keep shrinking that until it's just like infinitesimally close to the point A. In other words, take the limit as h gets as small as possible for f of a plus h minus f of a divided by a plus h minus a. Well, that would just be h. This, fun fact, this is the value of the derivative at a point A. So if you let A be any value x, then this is the definition of the derivative as a function. And derivatives are the beginning of calculus. So this is a little bit of calculus that you're asking about, I think. Or it's at least a problem that's giving you a glimpse toward calculus. Like in the future, with this type of problem, you think of h being infinitely close to the point A, so that it doesn't even show up at all. This is the slope of that graph at that one point. Oh, you have 2 weeks left in pre-calc, test Monday. That makes sense. This would be like one of the last things to learn in pre-calculus. Yeah, man. Because this is actually quite literally like the beginning of calculus. So it makes sense that you would learn this at the end of pre-calculus. Yeah, that totally makes sense. Cool. Well, I mean, it's a bit off topic, so... Oh, yes, please. Yeah, HHH Tau family, I apologize if you've been waiting to ask that. Please drop questions in the chat and line things up, and I'd be happy to work anything. I have to disturb the poor Luna. She's sleeping on my book, but she can get over herself. Sorry, Luna. Sorry. Okay. Yeah, go back to sleep. She's going back to sleep now. All right. Page 386, number 2. No. Oh, you enjoyed the calculus review. Great. Okay, so we're going to look at 386, number 2. It sounds like we're going to do an induction. Heck yeah. Awesome. Okay, yeah, let's do it. Thank you. I'm glad you asked about induction. So this is Lang, chapter 16.1 on induction. And specifically, this is on page 380. Oh, wait, 386, right? Oh, yeah, 386, number 2. Cool. I love induction. Like, I just think it's such a powerful technique. We use it in all over math, everywhere. Like, do induction on the dimension of a vector space. You can prove this by induction on n or something. Like, we just use this technique all the time. So even though the proofs are not quite as pretty and clever as Gauss's argument, this strategy is so useful. Like, it's like truly one of our most important techniques of proofs. So prove that for all integers n greater than or equal to 1, we have part A. Yes, this one is lovely. I thought about talking about this. I was going to save this for my next examples video. I'll still work it in the next examples video. But this is a lovely one. Well, the first one's okay. The second one is the one that I find is really beautiful. The first one is fun. It's like kind of like a twisted version of the fact that we were working before, but this time we're working with the square numbers, right? So I'm just going to jump right to the proof, but in my demo coming up in the next examples video, I'll give some more calculation practice with this one. But so we prove this by induction. You could start your proof with a little sentence like that. Induction. This tells the reader, here's what we're going to do. We're going to do an induction argument here. The claim is true here. I would say the base case, sorry about that. The base case is true as 1 squared should be equal to 1/6 times 1 times 2 times, since there are like a few terms in this, 1/6 times 1 times 1 plus 1 times 2 times 1 plus 1. I would probably just write this temporarily. This, on the right-hand side of the formula, what I'm doing is I'm substituting n equal 1 everywhere into this equation. We get 1/6 times 1 times 2 times 3. Well, yes, 1/6 times that is 1. So both of them are just equal to 1. 1 squared is 1, and the right-hand side also equals 1. If I want to clean this up just a little bit, there's like 2 presentations that I do. And I don't know there's no answer on which one is better, like how to write this, like stylistically. We could say that the left-hand side is 1 squared, which is 1. And then we could say that the right-hand side would be 1/6 times 1 times 2 times 3, which is 1/6 times 6, which is 1. Thus, left-hand side equals right-hand side, and the base case is true. The claim is true. It's fairly verbose. This is verbose, but in an intro to proofs course, I think I would want to do details like that. If you wanted to be like a little more succinct, because you feel that that actually makes the proof more readable, you could say the base case is true as 1 squared is equal to 1/6 times 1 times 2 times 3. Like, writing this shows that you've thought of what the left-hand side value is and what the right-hand side value is. And maybe both of them equal. They're all equal to 1. I would like this one, this presentation. I think that's nice. And then sometimes an author will just say that the base case is clearly true. Or just say the base case is true and not even show the details. But in any case, this is the... When we're proving things by induction, or like learning how to prove by induction, we want to fill in those details. All right, next, more importantly, for the inductive step, part 2, assume the claim is true for what is this? N plus 1, N plus 2, 2n plus 1. So assume the claim is true for up to an integer n. Then we check whether the claim is true for the next number. 1 squared plus ... n squared plus the next number after n on the left-hand side would be n plus 1. So the version of the left-hand side for n plus 1 is this. And by the inductive hypothesis, we assumed that the first n sum and have this property. It's true at least for the number 1. So we're allowed to make this assumption that it's true for some number that's at least 1, because we've shown that it already is true for one of them. Okay, now it's a little tricky, but we'll do it. We haven't worked with a lot of polynomials and distribution of especially a degree 3 polynomial. So what you may or may not remember the foiling approach. This is like a double distribution method. We just use the distributive property twice. For the first two terms, we get n squared plus, we will get 3n plus 2. And then 2n plus 1. Plus n plus 1 squared, which is n squared plus 2n plus 1. Again, you can see this one by distribution. Or Lang's formula about the sum of, or the square of a sum, which we've proved. This is 1/6 times doing distribution. I'm going to do 2n times each of these and then add 1 times each. So 2n cubed plus 3n squared plus 4n plus n squared plus 3n plus 2. Now we only need one parentheses plus n squared plus 2n plus 1. Okay. This is 1/6 times, let's combine like terms. There's only one cubed term, so I can write that down. 2n cubed n squared terms. There's this one and this one. So 3n squared plus n squared is 4n squared. N terms, there's plus 7n, and constant terms. Now, because I want to combine these two, ultimately, and my goal is to get in something in similar to this with a 1/6 factor out. I know that for the second term, I'm going to want to convert that to have a denominator of 6. So I would need to multiply everything in this by 6. This is just, multiply the numerator and denominator by 6 as an idea. Now I can take out that common factor of 1/6 and combine like terms. So cube terms, we only have the 1, 2n cubed. N squared terms, we have both of those. 4n squared plus 6n squared. Constant terms is going to be 19n. Oh wait, no, sorry, linear terms. And then constant terms is 8. Okay, so now here we've got two methods here. One, you can figure out how to do polynomial division and factor out terms. That's going to work if you know that theory, and you can look at the chapter on polynomials to see polynomial division or factoring. There's a synthetic division method that's very useful here. This is like strategy 1. I'm going to take a different strategy, actually. All of this was showing what the left-hand side is. This is all the left-hand side of the claim when n is n plus 1. Right? This is our claim for n. Let's come back. Let's come all the way down here. This is the claim for n, and we've been working from the left-hand side another strategy is to work from the right-hand side and meet in the middle. Like, show that the right-hand side equals something and the left-hand side equals the same thing. Then, therefore, you get the whole... Then you know that the left-hand side equals the right-hand side. So, the left-hand side is simpler. The right-hand side, every n changes to be an n plus 1. So 2 times n plus 1 plus 1. I replace that n with n plus 1 in that last term. If I factor through, we get 2n plus 2 plus 1. That's the same as 2n plus 3. So I want to start actually from the right-hand side and then end up showing that it matches this. So we meet in the middle. The right-hand side then would be 1/6 factoring or distributing these two together. We get n squared plus 3n plus 2 multiplied by 2n plus 3. Now, I'm just going to do it as the distributive method. 2n times each of those. 2n cubed plus 6n squared plus 4n. And then 3 multiplied by each of these. Plus 3n squared plus 9n plus 6. This is 1/6 times 2n cubed plus 6n squared, and 3n squared is 9n squared. 4n plus 9n is 13n. Did something go wrong? Plus 6. Those numbers don't sound as familiar as I was hoping. That doesn't sound right. What went wrong? Oh, wait. I messed up. Oh my gosh. Okay. I messed up the claim on the left-hand side. Alright. I apologize. I feel like it's maybe because I'm working on an iPad or something, and I'm just not seeing all the lines at once. The original claim, I've forgotten this. I don't have this one memorized. This one just doesn't come up as often in the real world. it's n times n plus 1, but here in the inductive step, here was my error. I said that this, I assumed that yellow part was the same as this. I got this part incorrect in the inductive hypothesis. Okay, so here I had n plus 1 and n plus 2. Apologies. This should have been n times n plus 1. Oops. Alright. Then this first term, apologies, would be n squared plus n. And then we still distribute. And these terms would be different. 2n cubed plus 2n squared plus n squared plus n. Right. Plus n squared plus... Oh, wait. Sorry. Okay, all of that term gets replaced. Because all of that is bound to the one... No. Let's just do it. Let's just do this again. Alright. Whoo! Alright. 2n... Yes. 2n cubed plus 2n squared plus n squared plus n. Right? Now, 2n cubed plus 2n squared plus n squared. This is 3n squared. 3n squared plus n. The second part still converts the same way. Now, we combine like terms. 2n cubed, there's no n cubed in the second term. 3n squared plus 6n squared is 9n squared. N's 13n and 6. And now we like call this middle or something. So we showed left-hand side equals ... middle. And then we ended up getting right-hand side equals ... this thing. 2, 9, 13, 6. 2, 9, 13, 6. So the right-hand side also is equal to middle. Therefore, left-hand side equals ... middle equals ... right-hand side. So the claim is true for n plus 1. When the claim is true for n, then the claim is also true for n plus 1. Therefore, it's true for every number. All right. Apologies for the misstep during that, but I think that we got it. The most important thing I think that you should take as a takeaway in this is that sometimes it really is helpful to work from the left, get to some point, and then work from the right and get to that same point. And then if the left-hand side equals a thing and the right-hand side equals that thing, then left-hand side equals right-hand side, and then you're done. So like meeting in the middle is a very valuable proof technique to prove inequality. Yeah, meeting in the middle. Yep. All right, so scroll down just for this part, I think, to show, or scroll the entire thing. Would you like to see the whole thing? You can rewind the video as well, but this is the bottom part of, this is the last part of the page. And this is just parenthetical. Like, we are done at this point. This is the, like, in symbols, really the induction strategy is this. We know that the proposition is true for 1, therefore it's true for some length, for some numbers, and then we showed that when it's true for one number, it's then true for the next number. So then P1 implies P2, implies P3, implies P4 for every single number forever. It's like the domino analogy, like Luna knocking over dominoes. Yeah. Hope that made sense. Thank you. Thank you for tuning in. It was fun to practice math with y'all today. Yeah, thanks for being here. Let's go ahead and wrap it up for right now, and we'll call it a day. Thanks for being here. Great to meet you all, or see you again. You're the man you are. Yeah, thank you. Yeah. Nice to see y'all. Bye. Take care.